Hello everyone, my name is Wending Mai. I am from the Pennsylvania State University. Today I would like to talk about our recent work about the prism-based DGTD with generalized dispersive model and its application to analyze the thin pixelized optical metasurfaces. Firstly, I would like to give a short introduction of why we would like to do this and how this is important for other researchers. And then I will give a derivation of the present DGTD with GDM formulations. And then numerical examples was given to validate the accuracy and efficiency of the proposed method. And then a short conclusion. Among various metasurface designs, pixelized metasurface represent one of the most popular classes. Here is some figures from literatures analyzing pixelized metasurfaces. Because pixelized metasurface can be readily designed using currently popular machine learning technique and other optimization techniques. And for machine learning and optimization, accurate and high efficient full wheel simulation technique is an essential part because pixelized metasurface design has a large number of variables. So efficient software can save you a lot of time for simulation. And the discontinuous Galerkin time domain method, so-called DGTD method, has become a subject of such much attention due to its high degree of accuracy, which comes from the flexible meshing and high-order basis functions. Moreover, it is efficient because it is suitable for element-wise parallelization. Therefore, it is widely used for many kinds of parallel computing, including GPU acceleration. And in DGTD, each element can be computed separately, which allows for a significant degree of freedom when comparing with other numerical methods. And the prism-based DGTD method is ideally suited for modeling planar geometries. It has been already proven to efficient and accurate method to simulate planar structures such as PCB board and AVS structures and metasurfaces. The basis functions of our prism-based DGTD can be defined in these ways. There are line basis functions on each side of the prism, and the basis functions definitions are given here. But to accurately describe the dispersion of gold over the optic region, here we employ a specific kind of dispersive model, which composed of one Joule term and two critical terms, which is called the D2CP model. And the Joule term and the two critical point terms parameters are listed in this table. And this dispersive model is then incorporated into the DGTD formulation using the auxiliary differential equation method. This figure gives a comparison of the relative permittivity of gold from the D2CP GDM model and the elementary data. The squares and the diamond stands for the experimental values, real part and imaginary part respectively. And the solid and the dashed lines represent the real and imaginary parts of the corresponding D2CP GDM model. And we can see the D2CP GDM model exhibit good accuracy over a broad bandwidth with the experiment data. And then by performing Galerkin tests over Maxwell equations and taking into consideration of the numerical flux and the proposed D2CP dispersive material, we can get the semi-discretized matrix equations. Though the first two have come from the Maxwell equations, and the third one is from the ADE method of the dispersive material. And we can see the parameters in the GDM, for example, the A0, A1, B0, B1 are listed in these ADE equations. And next, the explicit Runde-Kutta method can be adopted to solve this matrix equations. And here is the numerical example. We apply this algorithm to analyze the representative pixelized metasurface, which is composed of a W infinite array of unit cells. This is the geometry of the pixelized metasurface. It is placed into our airbox, and our magnetic current excitation with modulated Gaussian beam is used for normal incidence. Firstly, we consider the response of the metasurface when subject to an X-polarized doubly incident illumination. The left hand is the transient response, and the right hand is the Fourier transformation. So we got the transmission and the reflection performance in wavelengths. And on the right hand, we compare our simulated result with the CST commercial software, which uses FEM method and experimental data. We can see both of these results matches well. Then we simulate the response of the metasurface subject to a Y-polarized illumination. Similarly, left hand is the transient response, and right hand is the performance in wavelengths. And we still got good agreement. So in conclusion, we propose a Prism-based DGTD method with a generalized dispersive model to simulate the pixelized optical metasurface efficiently and accurately. The accuracy of the proposed algorithm was analyzed by comparing results with numerical examples of a gold pixelized metasurface. And this simulation tool with the proposed algorithm has been released online, free to public. And the users can customize the patterns and to analyze their pixelized metasurface with their customized geometries. And the toolkit is available in below web link. Thank you.